all the stuff to do with degree measures first. So we're going to do 13.1, 13.5, 13.6. Then we'll come back around and start talking about radians. Yes, ma'am? I don't have time now. So, you'll get over it.
I'm sorry, guys.
Tomorrow. I got stuff to talk about today. So we're going to talk, we'll go into the good old Chief SOHCAHTOA stuff a little bit. And we're talking about the SOHCAHTOA. What does it stand for?
Cosine.
Opposite adjacent. You write slow. Did you just say that?
All right, so when you're dealing with trig stuff, in this class or in this book, they usually use the symbol theta for your angle instead of the old angle symbol. So that's what theta is. Now, in a right triangle, theta can be either one of your two either one of your two acute angles in the right triangle. One part of the right triangle that never changes as far as side lengths are concerned is the hypotenuse. The hypotenuse will always be located across from the right angle. That doesn't change. Your opposites and your adjacents are the ones that change depending upon the perspective, depending upon what angle you're at. So if you're there, your opposite is this side, and your adjacent is here. And that's your typical setup for trig that you guys have been working on for a long time. You guys did that over and over and over again last year. Well, what we're going to do is introduce you to what are called the inverse trig functions. There are three other trig functions that we deal with in Algebra 2.
Oh, is that the sine to the?
That's called arc sine. When you're trying to find you're right, we called it the inverse button. When you're trying to find the angle, you use the inverse sign because it's sine to the -1. What that is in the calculator is considered arc sine. What we're talking about here are the inverse functions.
Oh.
The inverse functions of them. Yes, sir.
Where does the law of cosine and the law of sine fit into all of this?
13.5 and 13.6.
Okay.
Exactly where we're doing next. All right. So let's look at what are called the inverse functions. When you're dealing with an inverse, what you're thinking of is taking sine, and it's 1 divided by sine. That's how you find an inverse. You make it a reciprocal. Well, if sine is opposite over hypotenuse, this means you get 1 divided by opposite over hypotenuse. And now it starts to become to look like one of those crappy complex fractions. But rewrite it horizontally. You get the same thing as 1 divided by opposite over hypotenuse. Now it doesn't look so ugly, right? Sure. And instead of dividing by a fraction, you multiply by its. So this becomes 1 times hypotenuse over opposite. So the inverse of sine is hypotenuse over opposite, and that is called.
Could you have just said that?
Well, I've shown you where it comes from.
Why?
Why not? This is called cosecant. Cosecant of theta is the inverse of sine.
So we have hypotenuse over opposite is the inverse.
Wait, this is called cosecant?
The cosecant is the hypotenuse over the opposite. It is the inverse of sine. Yes, sir.
What's that weird 8-looking thing that keeps?
That is called theta.
Oh.
It's a 0 with a line through it. It's
All right.
theta.
Oh, I didn't draw that one.
The inverse of cosine is secant. Secant is the inverse of cosine, so it is hypotenuse over adjacent. And then lastly, the inverse of tangent is called cotangent. and that one is adjacent over your opposite. So what happens here is you're basically flipping all of your fractions and giving them new names.
What's the last one?
Cotangent. So it goes sine, cosine, tangent, cosecant, secant, cotangent.
Secant, get the cool name, and cosecant, and cotangent, have to take the co. That can be,
I don't know.
yeah, you can change.
I don't know. I don't know. I wasn't there when they named them.
I don't know why I just think that sounds.
I took that day off of work.
Yeah, maybe that sounds like-
What this is going to allow us to do is write out trig functions in terms of ratios. It's not going to make anything really all that scary, difficult, bad. We're just going to be able to write out all 6 functions. We're not finding angles or anything yet here today with this stuff. You're going to take a triangle, and let's say it's, well, obviously it's a right triangle, so that's what we're working with. Let's say we'll have our theta, and let's say this is 2 root 2 and a 4.
So the angle's theta?
The angle is theta. How do you find the hypotenuse?
Wait, is it theta or theta?
Theta. That right there. So what's your hypotenuse here?
Facebook is 4. No, one more time. I just see a little random number.
What's 2 root 2 squared?
8.
8. What's 4 squared? What's 8 and 16?
24.
What's the square root of 24?
2 root 8. I'm just saying a random number.
Okay. You get 2 root 6. Do you guys remember how to simplify radicals with your calculator? Remember the trick?
No.
We all agree that to find this one, you did this plus this, you got 24, right? You take the square root of 24. In your calculator, if you put it into your table, y equals, type in 24 divided by x squared. Go to your table. As you go through your table, you're looking for the smallest value integer-wise before everything becomes all decimals in the y column. Notice how you have 1, 24, 2 and 6, 3, 2.6, 4, 1.5, and so on. That means 2 root 6. Okay. That's how you can simplify these two.
Wait, where do you generate
like no one told me anything.
See how it becomes all decimals after that? So that 2 and the 6 with the last integer is 2 root 6. It's a nice little trick. Okay. So if I wanted to list out all 6 trig functions then of theta, sine of theta would be 2 root 2 over 2 root 6. Do you agree? What do you have to do then?
Rationalize.
Simplify and rationalize. What can you do right off the bat to simplify?
Cancel out the 2s.
The 2's. Now, what's the trick then for the root 6? Remember?
Multiply root 6.
Yep. Just multiply top and bottom by root 6.
2 root 3.
What do you get in the numerator?
2 root 3.
Correct. You wind up with square root of 12, which you should remember is 2 root 3. And you get that. There's your sine. 2 root 3 over 6. You go to the cosine.
Could you reduce it to like?
Oh, I'm sorry. Oh,
3?
yes, then it becomes root 3 over 3. Yep, thank you. So the sine in this case becomes root 3 over 3 when you simplify it all out. You do the cosine. So we have 4 over 2 root 6. So that becomes 2 over root 6. So it's 2 root 6 over 6.
Wait, how does it become root 3 over 3?
When you multiply, this was root 12, which is 2 root 3, and it was over 6, so 2 over 6 is 1/4.
Yes, I do.
It's just simplifying it with some fraction stuff. Tangent, opposite over adjacent. What did I say it was, 2 root 2? So this just becomes root 2 over 2. Okay?
What is that? Is that for? Over.
It's 2 root 2 over 4, yes, for tangent. And then if you do all of your inverses, all you're doing is just flipping all of those fractions. That's all we're looking at doing here today. It's just write out your new fractions.
I got lost trying to write all that down.
Well, I didn't move it yet. Your cosecant is just the inverse of sine. If this was my sine was root 3 over 3, my cosecant would be
3 over root. But that doesn't fit the math ticket.
Fix it.
and you fix it.
Aw. Can't we just live that way?
So you have 3 root 3 over 3, which is root 3. Okay? Remember, I'm showing you worst case scenario right now with all of these roots. Most of it is not this tough. Figured to get you with the yeah, because root 3 over 3, this 3's drop out. Secant in this case,
Like, is that 2 root 4 or 2 4? 24.
where?
In cosine of theta.
This was 4, I crossed it off to be, because it's 4 over 2, so it just becomes 2. Here, if you go back to your original, it was already unrationalized. This is sometimes a little shortcut. We had it originally as 4 over 2 root 6. That was our cosine. The secant then would be the flip of that. 2 root 6 over 4. Simplified right there. You get root 6, oops, over 2. There's your secant. If you rationalize 3 over root 6, you'd get the same thing. Same idea here when you go to your tangent, your cotangent. You're just rationalizing it out again. The cotangent would be 2 over root 2. Apply it out. And you wind up with 2 root 2 over 2, which is just root 2. What's that called? Yes, ma'am.
Why did you use a 2 root 6 over 4 instead of the root 6 over 3?
See how this one, secant is the inverse of cosine. Cosine is adjacent over hypotenuse. This is hypotenuse over adjacent. I went right to hypotenuse over adjacent because I didn't have to rationalize it. I just showed it a different way to do it. Because you can always go back to your triangle and redo it off that.
So you would get the same answer.
You will get the exact same. If you do it right.
In like a test or something, would you ask for all of these?
Good question. On a test or assessment style, usually what I do is I give you the following information. I will say that the secant of theta is 8 over 5. What are the other 5 trig functions?
So that's disgusting. So sine would be 5 over 8.
Nope.
Cosine would be 5.
Yes. What I'm doing here is I'm giving you values, and I'll say secant of theta is 8 over 5. Secant is what over what?
The hypotenuse over adjacent.
All right, so secant is your hypotenuse over adjacent. So what I would do is I would draw up a triangle, pick a theta, and label it. Knowing that this is my hypotenuse, this is my adjacent, could I figure out my opposite?
Yeah.
What do you get? Which it is. So it's 39, right? And I don't believe you can simplify that.
Could we just do Pythagorean here?
That's exactly what I just did. It's 64 minus 0.5. So now you know your opposite, and could you fill in the blanks then? That's what you're looking at doing here. Can you take a given statement from one of the trig functions and fill out the blanks? Okay? That's what we're looking to do with this. That's the new stuff with this. Does that make sense? The other part that we go back into reminding ourselves of are
Special right
right
triangle.
triangles.
I remember those.
Okay. Now,
45, 45, 90.
so you have your 45, 45, 90s,
And
then your 30, 60, 90s.
I was gonna say 60,
Q,
30.
Q, and 3, 2, Q.
Okay.
Oh,
Now, if you remember, what were the ratios of the sides for 45, 45, 90? How'd you guys write that out?
Q, 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 and 2.
Yes, but I use X's.
This is like my favorite chapter. I remember all this stuff.
He uses Q because a lot of times in the book you're solving for X,
Okay.
and X might not be this value X.
Oh.
That's all. And it's not a bad idea. I just creature of habit. Same thing with the 30, 60, 90. Cross. Sorry, go ahead. Go ahead. Q. Then what? Very good. Now, what we do in this class then is we take the two special right triangles and everything else after 13.6, we start over at 13.2 and 13.3 and 13.4, and then we go to 14. All of that stuff is really based off of these two triangles. Everything we do is based off of these when we go into radians, because we find all the trig values of these, and you're going to know them off the top of your head. All right. So let's walk through the trig functions, the 6 trig functions of a 45. And when I do this special triangles in the 45s, trying to find my 6 trig functions, I'm going to use 1 as my sides. 1, 1, and root 2. What's that, sir?
So this is for the 45, 45, 90?
Mm-hmm. We don't worry about any of the 90-degree angles for quite yet. We'll worry about those when we get to our trig stuff, when we get to our unit circle, when we start talking about the quadrantals. So what I do, quadrantals. Quadrantals are your axes.
Still sounds cool to say quadrant.
So if I want to look at the sine of 45 degrees, sine would be opposite over hypotenuse. In this case, it would be 1 over root 2. So what's the sine, though, when you simplify it out? Good. Cosine is the exact same thing, isn't it?
Tangent is 1.
Right. Tangent is?
I remember
One.
that was easy.
Cosecant then, notice how the cosecant is the inverse of sine. If sine is opposite over hypotenuse, cosecant would be hypotenuse over opposite, which is root 2. Secant of 45, exact same thing. Then what's the inverse of 1? 1. Okay. That gets us started. Now, in the 30s and the 60s, we do the same idea, but we use 1, root 3, and 2. Okay. I'm just going to do the sines of the 30s and the 60, and we'll worry about you guys can worry about the inverses. Yeah, I'm just going to start you off with the regular functions of the 30s and the 60s. So sine of 30, what?
1/2.
1/2. God bless you.
Thank you.
What would the cosecant be then?
2.
2. Okay. What's the cosine of 30? 3 over 2. And then the tangent of 30. 1 over root 3, so it's root 3 over 3. Okay.
First mistake.
Now notice what happens when you do the sine of 60. When you're at the 60, now what's your opposite? It's your root 3 over 2. When you're at your 60, what's your adjacent? Think about what's happening. You're just changing position. You're just changing sides. Instead of being opposite now, you're opposite here. The values within the triangle for the side lengths didn't change. Just your perspective on the angle that you're at changed. And this is what's going to allow us to build our unit circle by walking out over 3 different angles, 30, 45, and 60. These 3 angles have ordered pairs as they go up because it's all built out of side lengths. And they alternate positions. It's pretty cool how it works. For the tangent of 60, it would be root 3 over 1. So it'd just be root 3.
That makes so much more sense.
Okay.
Talk about the way it's the other quadrants, it switches.
Yep. So now as things go through, those values don't change. They're changing horizontally or vertically as they go around. And that's why their signs, SIGNs, change in the different quadrants.
Yeah, that makes sense.
Okay? Because each one of these is built off of its own, what they call a reference angle. And that reference angle off of each of the quadrants, the quadrantals, the axes, that reference angle never changes, therefore that works.
Now it goes together.
It comes around full circle.
That's a good one.
That was bad.
This makes sense for us to-
Oh boy! I tried not to use my sarcastic sound. Oh boy! What do we do now?
You just use your like.
I was crazy.
I did not try to talk like that. I tried
you
to,
did.
but I went, oh boy! I tried to make it sound like I was excited about it. Instead of being, oh boy, what do we do now? I don't know. I'm trying to avoid doing that because the 3rd hour makes fun of me.
Like if
Izzy doesn't make fun of it. Guys, you should have the answer already. What's the answer? 5 root 3. It's a 30, 60, 90.
It is, I swear.
Why?
I get it now. I totally noticed this on the third degree.
What happens a lot in this class, especially as we get to law of sines, law of cosines and things, you guys have a tendency to overthink the obvious. True. That does happen quite often. Don't outthink yourself. If it says solve for x and you know it from the 60, you're probably, oh, I should probably use sine because it's opposite. My hypotenuse is there. If you have a right triangle and you're throwing a 60, you know it's a 30, 60, 90. Take another day off, would you? So if you're given across from the 90, my bowling score, a 60. In 2 frames.
my test
Oh. So if I'm given across from the 90, that means it's double what's across from the 30. So half of it is 5, throw a root 3 next to it, and you're done. It's magical. It's not magical. Same idea of what you guys worked on last Thursday. If you recall on Thursday when I had you guys solving the triangles, this is when you solve for all of your missing parts. And one thing that you guys were doing that I tried to remind you of was to make sure that you reuse your given statements. Now, we didn't go into great depth on Thursday about why that was happening because I wanted you guys to kind of work on your own on this. But I want to show you what can happen. So if we have a right triangle, you're given an angle and a side. When you fill in the blanks there on your diagram, you know whether or not it's an opposite or an adjacent or a hypotenuse and going from there. In this case, we know we have the angle and the side opposite it. From there, you also know that you have to find two sides. In this diagram, given what I know, I have to find a hypotenuse and an adjacent. Right? The other angle is easy. It's the complement. So it's got to be what? Well, maybe it's not that easy. So the complement is when they add up to 90. So 90 minus 20 is 70.
You said the wrong number?
Yes, he did.
Oh my gosh.
So here's what happens. I want you guys to get in the habit of writing down what you're doing before you press buttons. If I'm going to find my hypotenuse, given the angle at the side opposite, what trig function am I going to use? Sine. Good. So I'm going to write this out. The sine of 20 is my opposite over my hypotenuse. Well, what does call that? Well, it's C in this case. Now, you may or may not remember what you actually did when your variable was in the denominator. Yeah, so you just flip-flop the angle and that unknown. So your value is 12 divided by the sine, 20. It's fraction equal fraction, you cross multiply and solve. That's the shortcut. Now, here's what I want you to do. You would write this out, and then you type it in your calculator. What happens if by some mistake you accidentally type in 12 divided by the sine of 22 and you write down an answer? It's wrong, right?
No.
No, but because you typed this in, you wrote and showed me what it was. You weren't a dope. Good. Now here's the problem. If you reuse what you did incorrectly to find your adjacent because you decided to use cosine with that hypotenuse, is there any possible way you're going to get that one right?
No.
It's slim, but no, you're not going to get that right. But if you reuse your given, what trig function would I use with an opposite and an adjacent? Tangent. So I would reuse my given and say, well, the tangent of 20 is 12 over that b value. So then I know that b would have to equal 12 divided by the tangent of 20. Guys, the reason why I say to do by reusing your givens, you run less of a risk of being doubly wrong. You could get one of them right and one of them wrong. You could get, if you get the first one wrong and you reuse the wrong, you're always going to be wrong. Because two wrongs don't make it right. But two lefts make the, three lefts make it right. Okay? So just make sure that you write down what you're going to type in before you do it. Now stand up. This is going to be awesome. Come on, Mal. Turn left 90 degrees. Turn left 90 degrees. Turn left 90 degrees. Did you just make it right? That was funny. Did you not understand
No, I got it.
Tom, stand up.
No, I get it.
No, everybody stand up. Levántate, por favor.
Okay.
Turn left.
Oh, look, I turned right. No, I didn't. I only turned left.
Actually, you just did it.
You just spun around and is it pirouetted? Was it? Is that pirouetting?
That wasn't pirouettes.
What's the pirouette?
I don't. I'm not done. I would dance
You thought about it. If you knew what I was going to say, I don't know what that looks like. I can't, my mind isn't so smart. No, what is it?
It's like it's going over the world, so I just sit and do this all period. My nose is terrible.
Angles of elevation and angles of depression. Do you remember what those are? Okay, well, we'll do that tomorrow. So,
I do an angle depression every day. And all that stuff over there.
I want to say it's 7:44. Here's what I got.
Geometry was the best year.
We have work problems in this chapter.
Yeah, there's quite a bit.
Can we not?
Nope, you have to.
I'm sorry, man. I was so mad. We talked about cooking all the free zero, and then I have a 10th-hour lunch. So I was like, and then we go to brunch, and I was like, a hamburger. And I'm like, stop.
Real quick, do you vaguely remember, by that I'm giving you some credit, I mean that nicely, it's sarcastic. How do you find the area of a regular polygon?
Base times height. Base times right
Measure
angle.
it.
You use the limit of that. The apothum, yes, the apothum. I call it apothum.
What is all mean? Does that just mean the 7 problems all? 7.
The area of a regular polygon. 1/2 the perimeter times the apothum.
Is it the line in the middle? It's the right angle.
Well, if it was the line to this vertex, wouldn't that be a radius?
It's the right angle height. Like say, it's the right angle.
I'm nodding just politely
It's the right angle height.
because I want you to figure it out.
So you're gonna like indirect. Just go with the general.
Yes, ish. You can figure it out. To those, we will talk more about angles of elevation and angles of depression tomorrow. What's different from what you guys did with angles of elevation and angles of depression last year is that this year you'll probably do a little bit more of the distances between things and stuff. That's right.
What is
That's